Welcome to The Explainer. You ever wonder how massive companies, we're talking millions of customers, millions of orders, manage all that information without it just collapsing into total chaos? Well, today we're pulling back the curtain on the secret blueprint that database designers use to turn all that messy data into an absolute masterpiece of logic. So let's start with a problem we can all kind of relate to. Imagine you're building an online store. You've got customers, you've got their orders, you have the products in those orders, shipping addresses. It's this huge web of connected information. So the big question is, how do you organize all of it so it doesn't become this, digital house of cards just ready to tumble at any moment? If you just throw everything into one giant bucket, like a single massive spreadsheet, you run into trouble almost immediately. You start repeating information all over the place, things get out of sync, and you basically create a system that's just begging for errors. It's not just messy, it's inefficient and incredibly fragile. And here is the key insight, the big idea. Just like an architect would never start building a skyscraper without a plan, database designers create a detailed blueprint first. And in their world, this blueprint has a name. It's called an entity relationship model, or as you'll hear it, an ER model for short. Okay, so let's break this blueprint down. The first building block is something called an entity. The easiest way to think about these, they're the main nouns in your data story. They represent the core objects or concepts you want to keep track of, things like a city, a county, or a state. Simple enough, right? But of course, just having a list of nouns isn't all that useful on its own. We need to show how they all connect to each other, and that's where relationships come in. If entities are the nouns, relationships are the verbs of our data sentence. They describe how these things interact. For example, a city is in a county. See? A verb connecting two nouns. And finally, to really flesh things out and add all the necessary detail, we have attributes. Think of these as the adjectives that describe our nouns and verbs. They're the specific properties, like the name of a city, its population, or maybe the acreage of a county. Nouns, verbs, adjectives. That's the core of it. All right, so we've got our basic grammar, nouns, verbs, and adjectives. Let's put them to work and see how this actually plays out in a real-world case study. We're going to design a database that maps out every single city, county, and state in a country. Now, someone new to this might just create one big cities entity and try to cram all the information into it. You got the city name, its population, the county name, the county acreage, the state name. You see where I'm going with this. It feels simple at first, but this approach very quickly leads to some really serious problems. And this slide shows exactly why that's such a bad idea. First, you get massive data redundancy. The acreage for Los Angeles County gets repeated for every single city within it. That's a huge waste of space. Second, the state's capital is just a word, it's just text. It's not a real link to the actual city entity. And this makes the data dumb. You can't just ask, hey, what's the population of the capital city? Because the system has no idea those two things are actually connected. And this is the elegant solution. We break it down, we create separate entities, one for city, one for county, and one for state. Then we connect them with those logical relationships we talked about, like in and is capital of. And just like that, the county acreage is stored only once, the capital is an actual link to a city, it's clean, it's efficient, and it's totally logical. Okay, so that was a pretty straightforward example, right? Let's level up a bit. Now we're going to tackle a more complex challenge, designing a database for a whole train system, one that has some very, very specific rules we have to follow. So here's the main rule, the core constraint we have to model. We've got two types of trains, local and express, and we've got two types of stations, local and express. Now, a local train, it can stop anywhere it wants, but an express train, well, it's exclusive. It can only stop at express stations. That's the rule. So if you took a simple approach, like just adding a type column to your tables, it would totally fail. And why is that? Because the database itself wouldn't stop you from scheduling an express train at a local station. It doesn't actually understand the rule. And what's worse, a bad design can accidentally create false rules you never even intended, like, say, preventing a train from stopping at the same station twice in one day. So how in the world do we solve this? Well, designers have a special tool in their toolbox for this. It's a kind of relationship called ISA. It's basically a way to model specialization. It lets us say that an express train is a specific type of train, and an express station is a specific type of station. We're creating official subcategories here. And by creating these subtypes, we can build a much, much more intelligent model. We can define a relationship that literally says only express trains can stop at express stations. The very structure of our blueprint now enforces the real-world rules, which means bad data can't even get into the system in the first place. Okay, so we've designed this really elegant blueprint, this diagram. It looks great on paper, but how does this drawing actually become a real functioning database that a computer can actually use? Well, that process is called translation. And translating those specialized subtypes we were just talking about, like our express train, is honestly one of the most interesting parts of the whole process. It's not always a simple one-to-one translation, and designers actually have three main strategies they can pick from. So, how do we get our express train subtype into actual database tables? This slide lays out three classic strategies. First up is the style. You create one table for all trains and then a second table just for the express trains, and you link them together. It's clean, but now a single train's information is scattered across two tables. Second is the object-oriented style. You create a totally separate table for local trains and another one for express trains. This keeps all the info for one type of train together, but now your master list of all trains is split apart. And finally, you got the null style. You just cram everything into one giant trains table and use null, which just means no value, for the express-only fields on all the local trains. It's simple, but it can get pretty messy. And here's the thing, there's no single perfect answer. It's all about trade-offs. All right, we've gone from diagrams to translation strategies. It can seem pretty complex, but really, all good design boils down to just a handful of core principles. You can think of it as a kind of philosophy for thinking clearly about data. And the first and maybe the most important rule is this: KISS. Keep it simple, stupid. It's a classic for a reason. More often than not, the absolute simplest design that gets the job done and meets all the requirements is the best one. It's easier to understand, it's easier to build, and it's way easier to maintain down the road. So if you don't remember anything else from today, remember these three things. 1. Avoid redundancy. Storing the same information in more than one place is the absolute fastest way to create errors and inconsistencies. 2. Capture the real rules. Your model should definitely enforce that express trains only stop at express stations, but don't go adding rules that don't actually exist in the real world. And 3, and this is a big one, use your common sense. These are powerful tools and principles for sure, but they are no substitute for your own judgment. So, to wrap things up, here's a final thought for you. Try applying this framework to something you know really well. Maybe it's your book collection, a video game you love, your favorite sports team. What are the entities? What are the relationships between them? You know, thinking about the world through this lens, that's the first step to designing a truly great blueprint for data.